and gentlemen, I'm pleased to welcome you here at the group exhibit Hydrogen Fuel Cells and Batteries at the Technical Forum in Hanover 2014. Please come in, have a seat, have a drink on the house and enjoy with me the next presentation dealing with the topic membranes, the central unit of energy storage and generation. And it's the same topic, but a different speaker. And welcome here with me the CEO of FuMA-Tech, Dr. Bernd Bauer. Give him a big hand.
So, good afternoon, ladies and gentlemen. Hope you are not so much disappointed that Dr. Jeske had no chance to present today. I will do my very best to replace him. So in the next 30 minutes I try to guide you a little bit through what we are doing in the field of energy conversion and in the field of energy storage. I try to give you some ideas about our company and our products, sum up with technical data. So just for those of you who have never heard about FuMA-Tech, we are a company located in Germany, part of a big water treatment group. It's actually the oldest water treatment group in Europe, founded around 1820 in the region of Mannheim, Ludwigshafen, in a nice town with the name Schriesheim. And our company, FuMA-Tech, we are the center of competence in membrane technology for our mother organization BWT. Most of our business today is membranes for water treatment. The future and where most of our R&D is done and where our turnover is increasing year by year is membranes for energy production, conversion and energy storage. That is one of the reasons why we more recently relocated to a town near Stuttgart, to Bietigheim, where we will open in 1 month from now. Most probably at least the largest membrane production or the largest production of ion exchange membranes, which is, let's say, built and in operation at that time of the year. It will be a casting line with 1.80 meter wide membranes, able to produce rolls with a total capacity of something like, let's say, 5 million square meter per year. Sure, not everybody will go, everything will go into fuel cells and batteries at the moment, but a big part of that certainly should go into those markets as well. So, just to give you a little bit of an idea what we are doing in our water treatment business in order to understand the business model of FuMA-Tech. So, in our water treatment business, we are typically making ion exchange membranes. That means membranes which are proton conductive or OH- conductor, mostly done on hydrocarbon materials, but also done for disinfection applications on PFSA, perfluorinated materials. And so our philosophy is to use a feedstock of raw materials, actually not too many, so maybe 4 different polymeric materials, and to use a production technology, which is solution casting and extrusion, which we are using in our water treatment technology and to use it in energy applications as well. Very often we deal exactly with the same product in our water treatment business, what we deal in our energy business. So when we talk with the water treatment guys on disinfection, we talk with the same product on the fuel cell side on PFSA membranes for fuel cells. If we talk about a chlorine-tolerant membrane for the chemical industry in HCl electrolysis, we talk about an anion exchange membrane for redox flow batteries in the energy storage business. So we try to use our volume production capacities and to bring them into the energy applications. Now, in energy application, our company strategy is a little bit different to what we are doing in water treatment. In water treatment, we make complete modules. In energy, we have a clear commitment to our customers that we focus on the membrane only. That means we do membranes for batteries, we do membranes for fuel cells, but we are not active on a stack level. Our supply chain, we start with monomers, we do polymerization, we make membranes, but we do not compete with our best customers, the MEA producer or the stack producer on a system level. So it's practically a membrane-only strategy. Now, if you are fixed on the membrane only. You need to have a bright and wide variety of different membranes. You need a bright portfolio. And so we use our, let's say, hydrocarbon and PFSA type membranes to have what we call our F-series PFSA type membranes for fuel cells. We have high temperature membranes, PBI based, which is our AM series. We have the pure hydrocarbon membranes based on a real polysulfone. It's our S-series membranes. And then we have our anion exchange membranes, which are going into alkaline water electrolysis and which are going also into redox flow batteries. I will come back to that later. Now, fuel cells, at least for us as a membrane producer, most of our business today is actually in collaboration with OEMs. So most of the turnover we do is typically going into automotive application. The number of customers, however, is much higher in the area of stationary fuel cells. But if you sum up the membrane area we sell on an annual basis, much more is going into automotive industry. Even so, there are not so many series vehicles available at the moment. So, starting with the stationary application, nowadays for us there's practically just one type of membrane which we recommend. It's based, as all of our competitors, it's based on a PFSA material, fully fluorinated, long side chain. So for those of you who are familiar with PFSA type polymers, in stationary application we exclusively recommend long side chain material. Different to our competitors, our material is by polymerization already stabilized. So the old discussion on whether you have a stabilized PFSA, a non-stabilized PFSA, we don't know. For us there is just one grade. By polymerization it's stabilized. So it shows the performance and the durability of, let's say, so-called post-stabilized PFSA, but ultimately done by polymerization. Range of equivalent weight, what we can produce is 800 to 1100. In fact, for flow batteries, we have even 1800. But most of the business in stationary, it's around equivalent weight 900. If you go into stationary application, you have a safety tool. For us, this is a reinforcement. So all of our membranes, without any exception, if you recommend it to fuel cell application, there is a reinforcement inside. Same with our competitors, we know. Everybody is using a different strategy to reinforce. For us, what you see here, we try to have a very thin reinforcement and to allow enough butter coat on both sides of the reinforcement so that you can seriously attach the electrode to the membrane and that it still allows, even if the backing has some, let's say, erecting fibers, still allows you to have a very low gas crossover and no let's say, pinhole creation by some erecting fibers. This is what we call our internal durability protocol. We do a lot of testing also with our customers on their own individual durability protocol. One standard test for us is to run hundreds of cycles between OCV and 0.4 amps per centimeter square, 85 degrees centigrade, 80% relative humidity. So these are the operating conditions for what we consider typical for a stationary fuel cell. And what you see here, even after 400 hours of operation, OCV is not very much reduced. We consider the material as being stable. If I would have done such a test, let's say 10 years ago, maybe after 200, 250 hours, you would not find any PFSA in the cell anymore because you simply depolymerize and oxidize. Nowadays, all the optimizations on fluoride release have finally resulted in a quite durable membrane which can take OCV for a long time. Even on OCV hold, which is for a long side chain material at 65 degrees centigrade but just 20% relative humidity, OCV hole test will not degrade the membrane even after 600 hours. Again, if you would have done a test like that, OCV hole, 20% relative humidity, you would have simply evaporized the membrane after 200, 300, 400 hours. And most important, after the test, if you look at the SEM, you see that the reinforcement has properly done the job it has to do. So the membrane thickness is practically maintained. I mean, on the first view, the SEM is looking ugly. This is coming off because there is a lot of, let's say, catalyst dissolution and catalyst migration in the membrane. But the most important thing, what about membrane thinning? You hardly can see it. So that is a typical autopsy. And what you see here, if we start with a membrane, typically 40 micron, you end up still with 39, 40, 38 microns. So membrane thinning is not really relevant after 600 hours of OCV cycling. What we do as well is the preconditioning and the post and the characterization after the testing. So begin of life and end of life. And so the difference between begin of life and end of life characterization under stationary conditions, I would say the performance drop is definitely acceptable. Now, next step, I mentioned already automotive application. In automotive application, there is one thing very different. The, let's say, operating regime is more challenging to the polymer. And in this case, we typically nowadays recommend the short side chain PFSA material, which is here indicated with SSC, so short side chain. It's again done by the same polymerization, also bipolymerization stabilized. The only difference is in the side chain and equivalent weight. That type of polymer allows you to have still, let's say, proper, robust polymer membrane with an equivalent weight of 700 to 800 without too much of dimensional change on, let's say, dry and wet state cycling. The big advantage of the short side chain material is the higher conductivity at relatively low humidity. Even in condensed water, you see that the conductivity is almost 30–40% higher than the long side chain, but the big change is coming if you reduce the relative humidity. So what you see here, let's say, forget about the total performance, because we are working with standard electrodes. For us, it's not to optimize the MEA in a sense to have the highest performance on the MEA level. For us, it's to get the most reproducible electrode to compare all our different membranes. So we use the same electrode technology for the same membrane. But what you see here, if you run such a short side chain PFSA material at low relative humidity, you can go up to 110 degrees centigrade at 30% relative humidity, and you still have, well, you see a performance drop, but you do not kill the application. So let's say the performance is not dropping down to zero at 30% relative humidity, which would be the case on a long side chain PFSA. And this is, I would say, the most important advantage of the short side chain material. You don't see it in stationary condition. So stationary, you don't need it. Mobile, we think it's a must. There is no other option from our point of view. If you do OCV cycling on the short side chain, same picture. OCV is maintained even upon dry. And if, oh, okay, so that's not there. But if you do an OCV hold test, it's the same thing. You can do OCV hold, 20% relative humidity, and the membrane keeps intact, is durable and stable. All right, so what else? High temperature membrane fuel cells is still an activity at our company. It has a long history since, well, almost 15 years. We are developing membranes and also help to develop electrodes for high temperature application, which we feel is most appropriate in stationary mode, running on reformate. We have a membrane unchanged for almost 10 years, which is a PBI doped with phosphoric acid. Different to what other companies are doing, it's a different type of PBI copolymer with a very much optimized retention behavior to the phosphoric acid, which allows us to have quite a nice performance and a good polarization with low kinetic loss in the low current region. So we can reach values more than 0.65 volt at 0.6 amps per centimeter square. And that was shown actually a long time ago already in the Japanese demonstration program, where we have shown on that membrane in smaller cells 30,000 operation hours stationary. So it's a boring curve. You find it in literature published by Samsung, where they were running that membrane for 30,000 hours within the MITI program in Japan. On top of that, we are doing all types of cycling on such a phosphoric acid doped membrane, and this is one of the key questions: how sensitive such a phosphoric acid doped membrane is against water, how sensitive it is on start-stop. And so we have a long list of different operating regimes, and one of the most challenging one is to have, let's say, to simulate a very wet reformate. Now, on our phosphoric acid doped membrane, the acid content is very low. We are below 2 moles of phos acid per repeat unit, so it's really almost covalently bound to the individual group, and leaching is very little. So you can run it even at temperatures around 140, 150 degrees centigrade wet, and you will not leach out phos acid. And that is the purpose of tests like that. Say that is one of the most challenging questions on all the reformate applications for stationary use. Now, last but not least, I would like to give you also some information on what we are doing in the field of energy storage. Because of time, I will not go into water electrolysis, so we are active in making membranes for water electrolysis. Today I decided to give you an overview, and I'm not sure whether there's a battery audience here, to give you an idea what we are doing in redox flow batteries. It's again a business we derive on our side from membranes which we are producing in large quantity for chemical industry in the chlorine business. An activity which we started, well, almost 20 years ago. Did the first installations around 94, 95. Have customers which purchase membranes for more than 50 years in various applications, but typically small scale, typically in the range of kilowatts, because there was no business model for energy storage in the past. Now, more recently, I would say in the last 3 to 4 years, you see worldwide more public interest in storing energy, and our main focus in energy storage is a redox flow battery, which is typically based on a vanadium type redox flow batteries. So we have customers which, for those of you who are familiar with that technology, which are on iron chromium. We have customers in the field of cerium, different redox couples. But what we see, especially in the last year and this year, that most of them now focus very much on the so-called all-vanadium redox flow battery, where you have on both sides of a membrane an electrolyte which is built from vanadium in different oxidation state, vanadium 3,5, vanadium 2,4. The big advantage of such a redox system is that you in principle have the same ions on both sides of the membrane, which means in real life everything is, let's say, not 100%. If there is some leakage through seals, through membranes, through whatever, you will not contaminate the other side, and this is considered to be the main advantage of those called all same metal, all vanadium-redox-flow batteries, where most of the R&D, I think most of that, it started in Australia, went to Europe. A lot of R&D was done in Europe, but most of the business nowadays is in Korea, it's in China, it's in Japan, where you have nowadays a typical installed capacity of such batteries, which is, let's say, in the round of 20 to 30 megawatt per year. Now, in our product portfolio for redox flow batteries, we have the old separator, and we still have customers which are using the old separator, which is practically a porous membrane made from polyethylene, polypropylene, or PDFE. And we have those customers which are using the typical ion exchange membrane, which are using either a cation exchange membrane or an anion exchange membrane. There is a major difference for the end user, because using a porous separator, electrolyte is in principle able to go from left to right, from right to left, and everything depends on pressure. On a cation exchange membrane, you have a flow which is all time going to the vanadium 5 side. Using an anion exchange membrane, flow is all time going to a vanadium 2 side. And now the key question is, how do you design your system, and what is the application? Is it peak polishing and you go to the megawatt range? Or is it, let's say, just to have intermittent current and you go to the kilowatt range? You can go for one or the other system, and I will show you now what is one of the decisive things. Said already, very short, porous separators, they are from polypropylene, they are from PDFE, and they are from polyethylene. Nowadays, I have to admit, only the iron chromium customers, which are going to the very, very, very low cost battery type batteries, which are targeting for what we hear, $50 to $60 per kilowatt hour, they go for a product like that. Customers which believe in applications where you have a lifetime of the battery approaching 10 years, let's say a good durability on cycling, and a good electrolyte management, they go for ion exchange membrane type systems. And what we actually offer is, it looks very complicated. In principle, it's very easy for those companies which make very big cells with very simple, robust cell frames with edges and whatever. They get a reinforcement thick membrane, and the reinforcement could be even in the range of hundreds of micron. And for those companies which have more injection molded or screen printed cell frames with, let's say, soft contact of membrane to sealing, they get what we call high performance membranes for high power densities. And especially more recently, if one of you is really involved in flow batteries, when it comes to the very high current densities, which are in the range of 200, 300, 400 milliamps per centimeter square, only extremely low resistant thin film membranes with 20 to 25 micron thickness, but reinforced. So all membranes are reinforced with a thin reinforcement can be used. And that is the way to improve the efficiency of redox batteries. And what we see from our customers, together with the new electrolytes, now slowly the cost of a redox flow battery with such a high performance membrane and high current density, it dropped from, let's say, 1,500 euro per kilowatt hour. Some of our customers are now approaching what we hear now, $300 per kilowatt hour. And some of them have even an idea to do it next year or in 2 years from now to reach the level of 150 US dollar per kilowatt hour. And then such a battery is really competitive for energy storage on large scale. For the customer, there are different parameters which are interesting. There is a so-called voltage efficiency, and there is the specific area resistance. So on a first view, it looks very boring, because voltage efficiency all above, let's say, except to that membrane, which we call our low-cost membrane. It's PFSA, it's equivalent to 1800. voltage efficiency is in the same order of magnitude. There is a difference in the resistance. So we have low equivalent weight material where you have only 0.4 ohm centimeter square, and we have higher equivalent weight material where you have 0.6, 0.7. More important is electrolyte management. For companies which build a battery, they would like to know what's going on with my electrolyte. It's going from left to right. How much is going from left to right on one charge? This is what you consider as electro-osmotic permeability. Now again, the cation exchange membrane have, roughly speaking, threefold higher electro-osmotic permeability than an anion exchange membrane. That means if you have a 1 cubic meter tank, you have to put a plus on your tank to take the additional electrolyte which is going from left to right. But after a complete charge-discharge cycle, it's almost zero. For an anion exchange membrane, it's not zero. Now, the big difference is, in a cation exchange membrane, you transfer only the acid. Here, you transfer the electrolyte. That means, if you do 1,000 cycles, here you have to rebalance the vanadium concentration. Here, nothing is needed. And this helps you to stabilize the performance of a battery. In a cation exchange membrane, there's almost no capacity loss. So capacity loss is in the order of magnitude of only .something% per cycle. In an anion exchange membrane, you have the capacity loss, which you then can recycle and keeps the vanadium level constant. Our recommendation here is, if someone builds a battery for a private house, 3 kilowatt, and his target is to make 1,000 batteries, he will not be able to service the battery because he will not be able to go from one battery to the other. Companies like that should go to an anion exchange membrane. Companies which make one big battery, peak polishing, where you talk about megawatt. Right now in Japan, we are discussing a 60 megawatt hour battery. So for them, you have a team on site. There's a service people, there's a lab. For those companies, they can go for a cation exchange membrane because they will do vanadium analysis anyway. And they have a chance to rebalance. And so summary is, well, you can have high performance with both membranes, cation and anion. The difference is only, and it's also the same order of magnitude on the total energy efficiency, which is actually pretty high with 90%. The only decision to make is for the customers how I would like to service the battery. If I know what is my service model, only then I can decide what is the right membrane. Okay, and with that I would like to stop and close, and I'm available for questions. Thanks.
Very much, Mr. Bauer, for being here and for this interesting presentation. But I'm sorry, we haven't got any time now to make some minutes for questions and answer. So I invite everyone who will discuss with you a little bit more and want to discuss a question, please come to the booth here at the group exhibit Hydrogen Fuel Cells and Battery, and the booth number is C71. I think you and your colleagues all will welcome everyone who want to talk to you.
Sure.
Okay,
thanks.
Thank you very much.
Thanks.